Thinking about it, almost there. All right. Hello, everyone. Thanks for joining us for this month's EPSP Connects. As many of you know, the purpose of this series is to bring the community together, to foster connections between people who might not be able to interact with others in a different setting. So we're very happy to have you here. I'd like to thank all the EPSP volunteers to help run this, people who handle the website, social media, who invite speakers, coordinate with them to make this happen. Thanks to all of you on the team. Joining me today as co-host is Shashank Anand, who will help us with questions.
Thanks, Roberto. And hello, everyone. Please use the chat to post your questions. Roberto and I will monitor them. And for those who are listening to us on YouTube live stream, we'll also keep an eye on it for questions. And you don't need to wait till the very end. So please feel free to post your questions as they come up.
Thanks, Shashank. All right, so today we have Dr. Sofia Alfeos. I don't know if that's the right pronunciation. Alfeos? How do you say it?
Alpheus.
Alpheus. All right, thanks for that. Dr. Alpheus is a fluvial sedimentologist whose research is focused on understanding the dynamics of river mobility and sediment transport in fluvial systems, particularly multi-threaded rivers, and its implications for stratigraphic architecture in ancient sedimentary deposits. Dr. Alpheus received her bachelor's and PhD degrees in geosciences from the Pennsylvania State University and is currently a geoscientist at ExxonMobil. Today, Dr. Alpheus will be talking about bed turnover in braided rivers. So over to you, Dr. Alpheus.
Great. Thanks, Roberto. And thanks to the committee for inviting me to give this talk today. I am excited to talk to you about some of the work that I did during my PhD working with Liz Hajek at Penn State. We were fundamentally looking at the controls on bed turnover in braided rivers, both, with ancient and modern perspectives. For most of this talk, I'll be talking about turnover, and we're thinking about it in a general sense as activation and deactivation of portions of the bed, kind of switching over of locations of the bed from a state of being wet to a state of being dry. And we're thinking about turnover in the modern and bed mobility in the modern as for insights into how we might think about mobility and form of braided rivers in the past. So to start, we're starting with this idea that rivers adjust their form to convey whatever sediment and water is supplied to them from their upstream catchments, right? And this supply of sediment and water is typically modulated by the controls of tectonics, climate, land cover, and also anthropogenic influences in the regions. Now, these levers, as they influence these river systems, rivers can occupy these different planforms all the way from meandering to braided river planforms. And typically our models are that as you change the sediment caliber, you might switch between planforms, and also as you increase channel gradients, so your slope of your system and your sediment supply, you might shift from a single-threaded towards a more multi-threaded planform. The thing is, if you just look at kind of the middle of this range of planforms, you see that there's a lot of range kind of from this anastomose to braided, this grouping of rivers. And we have all of these different forms. And one of the big questions is, how does this variance in form really reflect the environmental conditions of the upstream for each of these catchments? And then if we look kind of at actual braided rivers in the modern, we see that there's a lot of variance, again, in this grouping of rivers. There's a lot of variance across braided rivers in terms of the sinuosity of the threads, the number of threads, how complex the braided network is. And a big question is, how does that variability reflect those tectonics, the climate, the the vegetation or the land cover, and also other influences in the catchment areas. And then if we kind of extend this furthermore, if we look at the category of braided river deposits in the ancient, we also see differences in the form of these deposits, the shape of these deposits, and the range of variability is similar to what we see in the modern. So the idea is that if we can better connect environmental conditions to form and mobility, both in modern and in ancient systems, we can basically do a better job at predicting how these systems evolve in active landscapes, and then also improve our ability to reconstruct paleo environments from the ancient stratigraphic record. And so this is a great goal, but it's very difficult to do this in braided rivers because there is so many scales of dynamics happening in these channels through time. So this is, again, an animation of the Brahmaputra River in India. And we can see that you have bars moving, you have bed forms moving, which we don't capture at this scale. We have the channel threads that are moving around the channel belt and the channel belt itself that is evolving through time. And one of the main problems is that we have little clarity on the feedback between these channel and bar morphodynamics just in these active surface systems. And so now this is like a simplified schematic, again, kind of highlighting a lot of those dynamics. We have threads confluencing, we have zones of thread splitting, we have a bunch of different bars, crossbar channels, mid-channel bars, bank-attached bars across our river system. And then these bars are accreting in all sorts of directions. All of these things are happening together at the same time. And so connecting all of those feedbacks together to tell how the channel evolves or how the bars evolve is kind of one big research gap that we have right now. And then to add to that, we're not really sure of how those dynamics influence stratigraphy. So then thinking how this plays into the ancient, we still have a lot of questions as to how specific mobility and forms in active systems could be reflected in the form and stratigraphic architecture of the ancient. And then when you add now the influence of changing climate, changing tectonics, changing anthropogenic influences and land cover, we don't know how those catchment conditions influence form and mobility, in active systems, and also how they might be preserved and reflected in ancient deposits. So kind of on both ends in the active and ancient spectrum, we really want to be able to connect environmental conditions, environmental controls to dynamics that we see in the rivers and preservation dynamics in the ancients. And without being able to do this, we're kind of really limited in our ability to connect across these active and ancient timescales, and also to use kind of the fluvial geomorphological record to reconstruct things in the past or say things in the future. And this has implications for how we think about natural hazard prediction, thinking about how form and mobility change, or will be sensitive to changes in climate, for characterizing subsurface aquifers, both for water storage, carbon storage, hydrocarbons, whatever. And then also in our ability to predict changes or to reconstruct changes on ancient landscapes, both on ancient planetary surfaces and the geologic past. So there's lots of motivation to kind of understand the role of environments and catchment conditions on form and mobility in braided rivers. But so to investigate this, or kind of in our quest to do this, me and Liz, we started with the first question of how do channel and bar movements in braided rivers influence bar preservation and influence turnover on the bed. So again, we're starting with a simplistic figure of a river. We're thinking about how all of these processes control or are reflected in the architecture of the stratigraphy. The other thing we're thinking about is how braiding intensity or the complexity of the braided network is also affected. It is also affecting stratigraphy. So throughout the talk, I'm going to be talking about the entropic braiding intensity, the EBI, and this is just a measure of the braiding intensity in your channel. And you can think that if you have a high EBI, you have lots of active threads that are kind of equally spaced or more equally spaced. If you have a lower EBI, you kind of tend towards a river that has kind of one dominant thread and maybe a couple other smaller side threads. But most of the flow is being partitioned through a single thread. And so to approach this question, what we did is we used a numerical model to simulate a braided river evolving under very constant flow and sediment supply conditions. We used the model NAIS 2DH. This is the result of our simulation being played here. The browns kind of reflect the bars in the system, and the blues represent the channel threads. And the model is really nice because then we can really zoom into zones of the channel. So we've now zoomed into this region of the channel here and see how the surface is evolving, how the channel planform is evolving, and then also how stratigraphy is being built through that. So this is the surface moving here. You can see this bar that's accreting off into the right. And this top line here is that the surface of the model. And it's building the stratigraphy that you see kind of underneath that surface. And so we can build full stratigraphic cross sections and channel belts, just like the things that we would see in the field. So this model really allows us to go between kind of surface and stratigraphy and think about how that stratigraphy might be reflected in active systems. So this is that bar that's being produced just in this example scenario. I've gone ahead, we've used shear stress as a proxy for facies. So you can think that these dark brown areas are low shear stress zones in the channel. And these light brown areas are high shear stress zones in the channel. So you'd get a lot of high shear stress facies like dunes, whereas you'd get kind of ripples and kind of plain bedding in these low shear stress zones. This facies insight is really important for allowing us to go between the model and the field now. So this is an example of a bar package that would be a similar scale to that we see in the model. And the facies, being able to map the facies in the model is really helpful to be able to correlate that with the facies in the field, or to contextualize that with the facies in the field. And so we mapped all of these bar packages in a bunch of cross sections in the model, and we were able to pull out all sorts of information about the packages. We can get information about their geometry, like I said, their facies. We can map this using mapping methods that have been used in the field. So we mapped preservation in each of the cross sections of the model, and we kind of defined preservation based off of if we have upper and lower bar facies. And then also the sigmoidal rollover of our bar deposits. So we were able to map that through all of the cross sections in the model. You can color on these preservation now and get a sense of how each of the different cross sections are being preserved. So like I said, this is an example of two different cross sections in the model. You see one is kind of mostly orange. The other one is mostly gray. And means that this section A is kind of more preserved than section B, which is right downstream of it, which is mostly truncated. And this preservation is kind of giving us a proxy for what that turnover and bed rewicking history in the system now is reflecting in the stratigraphy. So for each of these cross sections where you see these magenta lines, that's where we produce one of these channel belts, we mapped preservation, and then we can summarize all of the information into kind of one bar plot that will show what the proportion of preservation is at this cross-section location. And so we did that for all of these channels, for all of these cross-sections in the model, and now I'll show you some of like the summary statistics just from this work. And so each of those cross sections is now represented by one bar in this bar chart. It's colored again by the same preservation. So if you see more orange, that's more preserved. If you see more gray, that's less preserved. And we can compare preservation throughout the model domain to things like braiding intensity. So again, that entropic braiding index, more braided is high numbers, kind of more single-threaded or towards more single-threaded is in the lower numbers. And then we can also think about how widening rate of the channel belts varies through time. And there's a lot of data on this slide, but I think one of the things that really stands out the most and is really most important to take away is that preservation is not particularly tied to any suite of braiding intensity or widening rate conditions. So if you just look at these two examples, you see one section is mostly truncated, one section is mostly preserved, but the braiding intensity and the widening rates are quite similar in these two locations in the channel. So they're experiencing very similar morphodynamics, but they have very different preservation histories. Similarly, if you look at these two locations, you can see that they have, again, the same approximate preservation or same approximate amounts of truncation at least, but the braiding intensity is now very different between these two zones in the channel. And similarly, there are differences in the widening rates in the channel. And so all zones in the channel kind of experience the same range of variability, but that is not or same range of conditions, but the way in which they experience those is not particularly represented in the preservation history. The preservation history kind of seems really random. And so to look at that in even more detail, we took those same two cross sections, section A and B. One was a lot more preserved than the other. And we looked at the history of the event history in those two locations in the channel. So these are now two wheeler diagrams for each cross section. It represents a time history of each location on the bed. So the bed is on the X, time is on the Y. And we have colored either erosion or hiatus of the bed by red if it's erosion, blue if it's deposition. And we can actually see a full written out history of what happened at that location on the bed. And so we see processes like threads migrating and forming bars where you see this prolonged blue depositional event. We see zones where you have threads migrating really rapidly and you have rapid turnover of the bed from that wet and dry state. You see that happening kind of mostly throughout this entire B section, whereas you have that happening really locally in section A. We also see zones of hiatus and abandonment, which we think facilitates bar preservation because you have slower turnover of zones of the bed. So where you kind of have nothing happening, these white zones, that's those hiatal events. And then finally, we can see avulsion happening in our channel. So avulsion is effectively where we end the model. So we can end the model at a bunch of different times and get kind of see the influence of avulsion on preservation in these sections as well. But kind of generally what we see in these two sections and across the model is that there's a lot of spatial and temporal variability in the amount of reworking and the location of reworking and turnover across the channel belt, both in one section and between cross sections. But fundamentally, it's the timing of those local events and the timing of avulsion that really control your preservation and reworking in the channel. So those were the insights, the two insights from the model. And again, the model was under these constant conditions. There was not much variability in the inputs to the model. So the question that we had is what happens if you perturb a system? So what happens if you have what is kind of the role of different environmental and landscape conditions on braided river form and mobility, and then turnover and reworking as a result. So we looked to the modern record and we got satellite imagery of 20 river reaches globally, and we compared that also with our model here. This is false color imagery again, and these are example reaches of the 20 rivers that we studied globally. And so we wanted to see how different environmental conditions, so the different catchment conditions across this gradient of rivers, how that influences their form mobility, their reworking, and their dynamics and their turnover dynamics. So these rivers, like I said, they're globally distributed. We have systems. Each of these circles represents the location of one of the systems. The circles are sized by the discharge and they're colored by sediment flux. So the more purple, you have more sediment flux. These are, again, all braided river systems, but they show kind of a range of discharges and a range of sediment flux conditions. If we characterize their mobility using area-based mobility metrics that sort of describe the rate at which the channel reworks itself, and then the channel belt, reworks itself, and the channel belt grows, reworking the floodplain. So thinking about how these channels are shuffling around in their belt, and then also how that belt is expanding over the floodplain. Using this example of the Brahmaputra here, you'll see that each of these rivers, the range that this mobility spans is anywhere from annual to centennial timescales, which is a really big range specifically just for braided rivers. And then on top of that, our traditional idea is that sediment flux really drives these mobility differences in these systems, but you can see that there's not really much of a clear trend with sediment flux across across these two axes. There's a mix of the purples and the light pink points kind of across the X and Y plot. So there may be a possibility that there are additional controls on mobility across these different rivers, or we might not be capturing the full mobility just with these two timescales. So that's one of the things we wanted to look at. So what we did is we collected pixel scale measurements of bed turnover, which we define as successive conversions between water and land of a specific pixel from 1999 to 2003 and 2023, sorry. We did this using Landsat imagery. So we have about 24 years of imagery for each river system, and we've characterized turnover in each pixel for each of these. So schematically, that looks like this. You have an image. We got median annual composites to minimize kind of stage variability in each of these rivers. So we have a composite image for each year. We've turned that into a binary land water mask. So the channel is now black, the land is white, and we track changes of those pixels from land to water. So for example, if you had a pixel here, you started off as water, then you were land for 3 years, and then you shifted back to water, back and forth for this time period. You have 4 turnovers, and they each span between 3 and 4 years. We tracked this turnover across every pixel that was wet by the channel through time, so through the active time period. So this white area is now this channel corridor over which we are tracking turnover. And again, that's just everywhere that the channel visits. That's a flooded area of everywhere that the channel visits through that 23-year time period. So this is, again, an example of the Brahmaputra, and I'm just showing you how that channel is wiggling around the channel corridor through time. We did this for the 20 rivers that I mentioned, and these all sample a range of climate conditions. So we are from tropical all the way up to arid, temperate, and then cold climate. So we get a good sample of climates, a good sample of grain sizes, and a good sample of variable plant forms, as you can see here. So now let's get into the results. What I'm going to show you now is how that white channel area, the proportion of that channel area that has been turned over through each time slice that we looked at. In general, the lines are colored by the mean number of turnovers, so like the turnover frequency. So more yellow means more active, purple means less active. And then on this y-axis is the proportion of that corridor, that white space that has been turned over through time. So each of these lines represents one of the rivers in our study area, or in our study data set. And what we found is that between 5 and 75% of the channel corridors are turned over during the 25-year period or 24-year period. So there's a large spread in the amount of reworking that is being done in the corridor, in each of these corridors through time. But I will say that if we just look at 3 sample rivers from this data set, we have the Lena, which is down here in the purple, the Amudarya, which is kind of in the middle of these lines, and then the Rakaya, which is up to the top of the data set, kind of our upper end number of turnover. There's very observable differences in both the spatial amount of turnover and the spatial distribution of turnover and the amount of reworking. So these white lines are now the boundaries of that channel corridor. And each of the pixels in this image, if the pixel has been turned over through time, it is now colored by the amount of turnovers that pixel received. So the Lena is mostly purple, and you can see that these pixels are only kind of colored around the boundaries of the bars, whereas in the Amudarya, kind of we have a lot more purple, a lot more of those pixels in the corridor are active. And in the Rakaya, most of the pixels in the corridor are active, and they kind of skew towards higher numbers of turnover through time. I think another thing that we found really interesting in observing this is that if you have fast turnover, that doesn't necessarily mean that you have more complete reworking. So there are parts of these channels, like in the Amudarya, there's parts where you have a lot of turnover happening frequently, but there's still large portions of your channel corridor that might not get reworked at the end of our observation period. So there's a lot of spatial and temporal variability across these river systems, and we wanted to look and see if there was any relationship with landscape or catchment conditions that could explain the trends that we observe on these plots. So we looked at 8 different catchment variables. We thought about the proportion of the sediment flux, that's bed load, unit discharge and sediment flux, slope, discharge variability over the 24-year period, vegetation cover, and we measured this using the normalized differential vegetation index from the Landsat images, EBI, again, so the braiding intensity, and then the ratio of those 2 metrics that I showed earlier, the time scale of channel overlap decay, and then the floodplain growth timescale. And turnover frequency is on the y-axis for all of these plots. And one thing that really stood out to us is that there's no predictive relationship that is like very discernible just across these 8 variables. And so that was surprising to us. We thought that there would be a lot more trend, but there was not. So what we did was we used a multivariate approach to test all of these variables across the turnover. So there's a lot on this slide, but just walk with me. We used principal component analysis to separate all of those environmental variables and to test to see how those variables are grouping our rivers and if there was any relationship in the turnover behavior with groupings of those variables. So again, those same 8 variables are our inputs. We have vegetation, braiding intensity, bed load proportion, slope, efficiency, discharge variability, discharge, and sediment flux. The weights of those variables are now represented on our PCA axes, are now represented by these arrows. So these arrows are long and point to the direction in which those variables define a lot of the trends or correlate strongly with the trends in the rivers. So if you have rivers that cluster up here, they are explained by high vegetation indices and high EBI. Similarly, if you are far away from that, you're probably less vegetated and less intensely braided. These plots, so each of these dots now, the size is, each of these dots represent a river, and the size is the proportion of the corridor that is turned over through time. So the smaller, you're kind of in the lower end, remember, like the Lena, where we didn't see a lot of the corridor evolving, whereas the larger you get, you kind of, most of your corridor is getting reworked through that time. And then the colors are now the frequency that turnover occurs. So we can already pull out some general trends in both combinations of catchment conditions and also combinations of rivers that behave very similarly. So you can see like this cluster up here where we have high vegetation and high braiding intensity. We have small amounts of the corridor actually being reworked and kind of infrequently being reworked. So we have small dots and purples. Whereas if we went down to the south, we have more of a discharge and discharge variability control on these groupings. We're getting larger proportions of the channel corridors being reworked and more frequent turnovers in these rivers that cluster down here. We can also, so we have these visual clusters that we can get from the PCA axes, but we can also cluster them quantitatively. And this is using agglomerative nesting to get clusters in these catchment conditions. And you can see that these 3 clusters of these variables are really well defined on these principal component analyses as well. So what we're approaching now are these families of environmental conditions that potentially dictate the mobility that we see in the river. So we've defined 3 styles of mobility based off of that turnover. We have this one style, which is this cluster off to the right here. We have a second style that is the cluster up to the north, and then a third style, which is the remaining rivers that are down to the south. And we'll look at each of those styles now in detail. Switch. Okay, so this first style we have here, we have the control of bed load flux. So we have increased bed load proportions and high slopes that form these really efficient rivers. And if you look at the turnover for most of them, you get really widespread reworking of the channel area and also frequent reworking of the channel. So we skew towards those yellow colors. A lot of those pixels are really active through time, and there's a lot of reworking being done in the channel. If we think about where these plot, these are kind of the most efficient rivers. So they're sort of, the channel threads are doing more work to rework themselves than to rework the surrounding floodplains. So we plot above this 1-to-1 line on that floodplain reworking channel overlap decay timescale plot. So we are these rivers kind of up to the top here. There's lots of activity. Most of the reworking activity is concentrated on the bed in this style of reworking. In contrast, we have this separate style that is kind of defined by high EBI, so highly complex networks, and large amounts of vegetation. And in this, we kind of get really localized turnover, and we have mostly reworking around the bars in some locations of the banks, but it's not widespread across a lot of the channels. If we think about where those plot on this axes, again, we are kind of in these longer timescale, less mobile rivers, kind of with more growth of the relatively more growth of the floodplain, but really we're just kind of approaching decadal to centennial timescales of reworking in these channels. So there's a lot less work happening over the same period of observation in this style, and it's a lot more localized and infrequent. And then finally, in contrast to all of those, we have this third style where we see kind of a zonation of the colors. So we see zones of these channel corridors that are more purple, zones that are more pink. There's a lot of lateral spread in where turnover is occurring. So we get a lot of the bed being reworked or activated through the period, but the frequency with which the bed locations are activated or turned over is very spatially variable. And these occur in systems that have high discharges and also high discharge variability. So they're a little bit more flashy. The planform often reorganizes itself during a lot of these high discharge events, and that results in this spatial variability in where reworking is happening in the system. So kind of with these axes, it's really nice because it allows us to kind of create more summary explanations of how combinations of environmental variables influence our systems. And it also kind of allows us to separate these different families of these rivers. And we can see kind of different sensitivities of different systems or different families of systems to certain environmental conditions. So we can start getting more nuanced observations and make more nuanced observations and kind of get more definitions on the expectations of mobility across these different environmental conditions, if that makes sense. So if we think back to where we started with this model that was just exploring reworking and preservation in unperturbed systems. What we saw was mainly stochastic. There was no real spatial control. There was no temporal control on where we were seeing that reworking behavior in the system. The reworking was kind of indiscriminate. And because of that, we got an indiscriminate record of turnover or an indiscriminate record of preservation. There was no way to correlate specific morphodynamics with specific preservation or reworking histories in this channel. What we arrived to by kind of taking the model observations and exploring similar measurements in active systems is that we are now able to define different styles of mobility within these braided channel belts that are combinations of specific catchment forms and conditions. So we have these three different styles that kind of respond to different levels in our initial like climate tectonics, land cover and anthropogenic influence. So if you think like style one might be maybe a little bit more tectonic influence, we have more bed load and higher slopes in these systems. Whereas if you increase land cover, you might jump into style two, or you might be dictated by kind of your bank stability that is formed through vegetation or maybe permafrost if you're up in the Arctic. And that leads you to have higher braiding intensity, or that allows you to sustain a more complex braided network and have completely different mobility than if you say you were primarily controlled by climate and discharge and your discharge variability, where you'd have completely different styles of mobility that would be kind of very laterally variable and kind of but laterally variable, but widespread across your entire channel corridor. And so in these styles, we can kind of even further divide out the turnover to think that like in style 1, you're primarily reworking the bed. In style 2, you're not really reworking very much on the same time scales of observation. And then in style 3, what you're doing is you're incorporating both bank reworking and bed reworking through time in these systems. And so kind of with these insights, we can now see that form and mobility in active systems really do reflect their source conditions in an observable way. And so we have a sense of what the sensitivity of active systems are to different environmental conditions. And then in the ancient, we can start to think of how differences in that reworking behavior, perhaps if you were like if you had an ancient system that had high discharge variability, you would expect more lateral variation in your preservation and your reworking of your ancient systems. You would look for facies that would be more reflective of that range of conditions that you can think of. And then, so to kind of conclude that and some takeaway points, I guess, is that braided river form is not a unique signal of specific landscape and environmental conditions. It's not one for one, it's a combination of a suite of things. And with that, kind of with the insight that you get from combining across scales, across forms, across catchment conditions, you can get better predictive power with kind of a more holistic approach to thinking about both mobility and form in active systems and also in the ancient systems. With kind of this information, you can do you can create more powerful approaches to think about sensitivity and mobility of systems in but as it pertains to assessing your hazards in active systems. You can have more nuance in how you model preservation and facies, and you characterize your reservoirs and your aquifers, thinking about subsurface fluid flow, contaminant transport, all those things in your subsurface with these more defined approaches. And then finally, thinking about ancient landscapes, with this broader context, you can pull more succinctly analogs from the modern to the ancient and then apply them kind of in the Earth's geologic record and also kind of on planetary surfaces. So yeah, and that's basically it. I'll stop there and I'll take questions. Thanks for listening. Ooh, what did I do?
Well, it's still a braided river, so.
Can you still see my screen? My screen disappeared.
We just see the monitor, not the PowerPoint.
Oh, okay. Well, yeah, so it's still a braided river.
All right, so
yeah.
Questions from the public, from the audience?
Ooh, okay. I'm gonna try to, there we go. That's what I was trying to do.
Do we have anything on YouTube, Shashank?
Don't think so.
Yeah.
No.
Thank you.
Just good feedback on the chat. Interesting talk. Thank you. Amazing visuals. Great talk.
I think we have a question in the chat from Emma. She's asking, did I understand right that higher discharge variability leads to wider channels or more lateral mobility?
Yeah, I would say we didn't look at channel widths in particular, but I do think it occurs in more laterally mobile channels. So whether that be your channels are just moving across the floodplain a lot more, or your corridor itself is widening, but you're definitely sampling more of your floodplain with higher discharge variability.
So I've seen some of this work before, and we've discussed this. You know, your analysis is based on annual composite images,
Mhm.
right?
Mhm.
Can you speculate a bit maybe on how the different regions, the tropical to temperate,
Mhm.
arid, might change if you did a seasonal focused analysis?
Yeah, so I think if anything, so we went through and basically with the composites, it samples kind of uniformly the hydrograph for a lot of those. In the ones with, I will say the ones with like the most variable discharge, we're kind of primarily sampling the low discharge stages. So let me think about this. If we're sampling low discharge, we might be oversampling turnover. No. I think we might be undersampling too. I have to do the math in my head. Um, there might be some changes, I think, with the highly variable systems, the systems with a high discharge variability. But I do think that because the systems are so large, the stage differences would have to be very, very pronounced to kind of alter the turnover statistics, because we're still capturing a lot of the variability. I think if anything, in smaller systems, we would be undersampling, but we're still getting that reworking behavior sampled, if that makes sense. I don't know if that answers your question.
I'm curious because the Pilcomayo River in the north Argentina and Paraguay, it looks like during the wet season, it covers the whole kind of
Yeah.
width of the
Yeah.
valley, and then as the dry season returns, the river is completely in a different location, and so I would definitely feel like dry to wet season is going to give you a very different
Yeah.
turnover rate for just this one system that I'm somewhat familiar with.
Yeah. So that, I think that was the point I was getting to about the size of the river, because I think definitely for those smaller systems where you like, if you turn the stage on and off, you're like having a couple of pixels that can have significant impacts on your turnover. So like in the smaller systems with higher discharge variability, we would expect that you are undersampling or underestimating how mobile the systems are if you're not capturing all of that. But even in the small systems, we see like the smaller systems are the most mobile of them all in our data set. So even if it is an underestimate of the turnover, we're still like seeing that mobility being recorded in the metrics. Whereas for bigger systems, like where we have the biggest problems is in like systems like the Indus and some parts of the Brahmaputra. But even in those, we are sampling enough of the system that even with those stage differences, it's not gonna influence. It doesn't shift the means, at least a whole lot with the reworking, if that makes sense.
Oh, there's another. So Shashank, can you share the question? Yeah.
Jasmine is asking, are the clusters from your PCAs similar to how you might choose to sort rivers into cluster if you were to do so visually as a geologist, or were your clusters somewhat unexpected?
I think the clustering I mostly agree with. I think some things are really surprising. I think one of the Yukon channels is like really well vegetated, but it falls like, I guess I could show you. It falls in this style 1 because it has a high slope and it's kind of confined to the floodplain. So there are some like nitty-gritty things that I am not not super comfortable with. I'm comfortable with them because they work out mathematically, but that I would visually not expect. But in general, I think they kind of fall where I would place them.
All right, so I just posted on the chat a question from a YouTube viewer. They want to know, now the big thing is wildfires, but even beyond wildfires, if you have changes in vegetation because of extended drought, or it could be wildfires, but anything that might cause changes to vegetation that might be holding some of the systems in place. So the question is, with these quick shifts and such, what do you think the most highly sensitive condition of these rivers is? And, can we keep them fixed as possible, keep local residents safe from things like sudden avulsions?
Yeah, I think that is something that we did try to get to when we were thinking about this work, because with these clusters, you can start to see specific catchment variables that might dictate how sensitive different systems are to different conditions, I guess. And so I think vegetation is one of those, particularly in these groups that have these very stable, complex braided networks. I think a lot of that is the bank stability that comes from the vegetation that is holding them together. So I think like a collapse in you would have to entirely collapse vegetation within the channel corridor before the systems would be starting to move differently. Whereas I think in some of these systems, if you added vegetation, if that would ever happen, you might start to stabilize and have less mobility and reworking in the systems. But then I think that in some of these other systems, the things that don't cluster in the cluster with vegetation, there are other environmental controls that they would be more sensitive to before you even changed like the vegetation in the system. So that is to say that things down here, which some of the bars are vegetated, but they're not as stable as maybe things up in this cluster. If you change the discharge regime, that would probably be something that would drive your systems to move completely differently rather than a collapse in vegetation, if that makes sense.
I'll ask the last one if no one else has anything else to add, but what's the one burning thing you couldn't do, that you would do next, if you find the time to do it?
I would like to do some sort of like harmonics analysis for each of the pixels. I think like it pains me that we rely so much on the means, and like the means are great. And just with the means and some information about the distributions, you can do a lot of this work, and a lot of that is captured in what we see. But I would really like to like for each pixel, you have like a wavelet of like how often it shifts from wet to dry or whatever. The timing, I would like to do something with like looking at the timing of changes kind of spatially in the channel, really map things to specific bars or to specific zones, partition out the turnover, and then also see how those time series, like even within one channel, across channels are changing. If that even like I can't even like word out what I mean, but like there's just so much variability that I think is captured. I'm just seeing Jasmine's message in the chat, but there's just so much variability in one of these systems, like with all these pixels, because you have so much data. I think it might be interesting to collapse them in different ways, not just a kind of across different systems, but like if you did just all of the pixels in the data set, all of those series, and see how that falls out. I think that could be informative as well.
Thank you. Shashank, maybe if you can share what we have for next month.
Thanks, Roberto. And thank you everyone for joining us today. And Sophia, it was a really nice talk. So thanks for sharing your research with us.
Yeah, thank you for the invite. It's fun.
Yeah. We are planning to host a virtual coffee hour next month so that we can bring people together who are interested in planning next AGU sessions. So if you have a session topic in mind or something that interests you, please try to join us in March. We are trying to figure out the whole details, and we'll share those details via mailing lists and social media as we typically do. So keep an eye on them. And yeah, stay tuned.
Thank you, everyone. Thanks, Sophia.
Yep, thank you.